everybody. Morning. We continue the weekly theme here. Let's do a chapter in one day. Nice thing about chapter 8, though, is it's short. They kind of, not sure why they did it this way. This could have been like the first 2 or 3 sections of chapter 9, really, put them all together. But so what we're going to do today, well, actually, for chapters 8 and 9, what we'll be doing is we'll be going through all of these toolboxes again, right? So these are the 4 toolboxes that we have learned together so far in physics. What class is this? 2A. So it says it right there at the top. There is a 5th, right? I've alluded to it. We'll get to that in chapter 10, okay? But basically what we're going to do today is we're going to go through kinematics for rotation. And then chapter 9 gets us into energy and Newton's laws and a little bit of momentum. So that's kind of what the overall plan is here. And my hope for you is that as we kind of go through these toolboxes again, that you'll parts of your brain will start firing. Where you're like, I didn't get that before, but now, okay. So hopefully that starts happening for you, because usually second time through, best time through. All right. So what we got to do, right, is we got to take all of that kinematics that we learned way back in chapter, 2 and 3, something like that, right? Okay. Back in the glory days when you thought class was hard. And what we got to do is we got to apply it to like this wheel rolling along. Okay. So we're going to do kinematics in rotation. But before we can talk about kinematics, we have to lay down some basics as to how we're going to talk about this. Because round things and things that are moving in circles don't naturally lend themselves to Cartesian XY coordinates. Like if we were to track a point on this wheel, let's say we put an ant on the wheel, right? Okay, and it goes around. I mean, we can sort of tell you what X and Y are doing at any certain point, but it gets really cumbersome. You ended up introducing a lot of trig and doing all kinds of stuff, right? There's a more natural coordinate system, and some of you are seeing the writing on the wall now and are a little bit afraid, right? But what's that coordinate system called where it's more natural for a circle? No, you chose not to remember it from your high school or okay. Well, let's lay this out here. Okay, we need a circle. Please make that a good circle. Okay, good. We made it a good circle, right? Okay, so there's our circle. I am gonna kind of lay down an X and a Y, right? Just so that we can reference back to it. But if I want to talk about the position right there on that circle, I can do it in X and Y, right? But the other way is to reference how far away I am from the center of the circle and at what angle it happens to be at. These are called polar coordinates. Okay, now that I've said it, is everybody going to freak out or anything? Did you never learn polar coordinates? Okay, you probably learned it in trig and then quickly forgot. Okay, so to be, instead of X and Y being a location, we can just say R and theta. So if I tell you that the radius is 1 meter and the angle is 90 degrees, well, where are you? Yeah, you're right up here, right? Okay. If I tell you the radius is 25 centimeters at 210 degrees, right? Well, then you're somewhere down here, right? Okay, so you probably ran into this. Maybe they didn't call it polar coordinates, but it very definitely is something that you probably were exposed to. Okay, so we're going to try to live, because circles and things moving in circles like wheels and tires and hard drives and whatever, okay, naturally fall into just being able to talk about radius and angle. We got to define some sort of more basic ideas here, right? Distance. How do we talk about how far something has gone. Like if it starts here on the positive x-axis and begins to rotate around, right? Is there a way for me to find out like the length of this arc right here? In fact, it's called what? The arc length. Okay. The distance S, right? That this point, this ant, whatever it is, the point on the wheel, the tire, the distance it rotated through in meters is called the arc length. Now, okay, so S is arc length in this context. This is what your book uses. What are the units of R, like the distance from the center? It's a length. It's in meters, right? Arc length is also in units of meters. So what do the units of theta have to be in order for you to get this to work out right? Theta has to have no units. What do we usually use when we talk about angles? Degrees, right? What's a degree? Yeah, nobody thinks about it, right? Okay, what's a degree? It's 1/360th of a circle. Well, that doesn't mean anything, right? So let's go one step further. What's the other way to do angles that nobody likes because you always put your calculator in the wrong mode? Radians. Okay, so what's a radian? Yeah, like Mr. Bailey, you asked me what a degree was. I didn't know the answer to that one. Now you're asking me a radian. I have no idea. Don't ever ask a math teacher what a radian is. They'll tell you something crazy and you won't understand it. Okay? So the unit comes from the definition of pi. Pi. Does anybody remember what the definition of pi was? Circumference of a circle divided by its diameter, right? Okay, it's true for all circles everywhere in the universe, know how big they are. Okay. What are the units of circumference? Meters, it's the distance around the outside. What are the units of diameter? Also meters, it's a length, right? Okay, what's a meter divided by a meter? Nothing. It's unitless. And yet, we will call the ratio, right, of the circumference of a circle to its diameter, we will just call that the number pi radians. What's a radian? It's a unitless unit? Tag? It's a tag. It's a hashtag. Hashtag radians. Right? Okay, like it's something that we humans put there because we were uncomfortable with just leaving a number. Where am I on the unit circle if I'm at pi over 2? Well, it doesn't feel right if you don't say pi over 2 radians. Or 90. I'm at 90 on the... 90 what? Eggplants? No. Degrees, right? Like, we throw this label on there to try to indicate that we're talking about circles, all that kind of stuff. But critically, the unit has no units. Radians is a unitless unit. It's very strange. I'm not responsible for it. And in fact, you're going to want to make sure that you're working in radians when we do angular kinematics. Okay? So how do we get from degrees to radians? What's our conversion factor? I can never remember if I'm going to multiply or do anything else. What's the conversion factor? In 360 degrees, how many radians are there? 2 pi. 2 pi radians. So that's usually the one I use, but you can say 180 equals pi, because if you divide both sides by 2, it's the same thing, right? Okay. So if we have, I don't know, 127 degrees, what goes in the denominator? 360. And what goes in the numerator? 2 pi radians, right? And there you go. You can find out what it is. Or you can ask Google, or you can just do it in your calculator. Like, I don't care. Well, not on the test. You can't ask Google on the test, right? But like being able to convert back and forth, it's going to be bread and butter for us. Okay, so we've kind of tackled units a little bit here, and we have this thing called arc length. With these ideas in mind, okay, we can now talk about the parts of kinematics, the very basic definitions that we use to describe how things move. What am I talking about? I'm talking about things like, let's just put the old friends up on the screen. The three equations, the three toolbox equations. Does anybody remember? V equals V naught plus AT. Oh, you remember that one?
X is equal to V naught T.
Okay, V naught T plus 1/2 AT squared. And then there was like a V squared. And then your book had a bunch of other ones, but these are the main three, right? Okay. So those were the linear ones. The toolbox could only deal with acceleration that was constant. But we needed to define, to be able to do this, we had to define like what's velocity, what's acceleration, what's position, all that kind of stuff. Well, we've got position down, right? Okay. So, what was velocity back in like chapter 2? It was speed. In chapter 3, we introduced the whole vector thing, which just messed up your life. But what was like kind of the definition of velocity? Its idea. Changing something over changing something. What's the thing that's changing? What's changing to get velocity? It was a change in position, right? Okay. We changed our position in time. It has units of meters per second. Acceleration was the change in velocity over time, right? But again, these are all like linear ideas. What does a change in position look like for a circle? Well, if I start over here and I rotate up, right? Did the position change? Yeah, it sure did, right? So angular velocity, right? The velocity something has goes in a circle. Like, could be that. That would be like a slow angular velocity. Why is this an angular velocity? What's changing? The angular position in time, right? I can make the angular velocity faster, right? This is a bigger angular velocity. So if this is what angular velocity looks like, what does angular acceleration look like? Yeah, the wheel has to speed up or slow down, right? You see how I applied the brake there and it slowed down? That would be an acceleration, right? An angular acceleration, because it caused the angular velocity to change. So what we need is a way to sort of translate these ideas that we had for straight lines into circles, right? And lucky for us, we do have Google Translate, right? Google Translate can get us from the linear to the rotational versions. And in order to do it, you have to learn Greek. So this is your Greek lesson for today, okay? Because what we're going to do, every symbol that we have, say for velocity, instead of writing it in its Latin and Arabic way, we are going to write it with Greek letters, okay? So what do I mean by that, okay? So for the rotational version, okay, our velocity, right? It's a change in what? Like, what's changing on a circle when it rotates? It's angle, isn't it? Right? The radius doesn't change. If you're out here on the outer edge, no matter where you are, the radius stays the same. It's the angle that changes, right? So our angular velocity is going to be a change in angle divided by time. And we're going to give that a new symbol. I need you to be very careful about this symbol, okay? Because it looks like something that you want to say, but you can't say it. There are two letters going on here, okay? What is this letter?
W.
That's a W. And how do you know it's a W? It's pointy. This is an omega. Okay? Greek letter omega. It's roundy. Okay? Now, I used to have anger management issues, and I used to throw chalk whenever somebody got this wrong. They come up, Mr. Bailey, my anger speed W. And I'd be like, piece of chalk. Right? When chalkboards disappeared, they gave us pens. Pens are awesome, but they hurt a lot more when I throw them. Don't be a target. Right? It's omega. It's not a W. Little pet peeve of mine. All right. I'm okay. All right. So, if we're going to use the symbol omega, right, to talk about angular speed, which is a change in angle over time, we can then change our omega in time, and this is going to be some kind of acceleration. If only there were a Greek letter that acted like the letter A. Alpha! Alpha looks like a little fishy.
Yeah.
Right? Okay? Told you were going to be learning Greek, right? But the concept, the core idea here is that angular speed is a change in angle in time. What is angular acceleration? It's a change in angular speed. So if something speeds up, it had an alpha. If it slows down, it had a negative alpha, right? And if the wheel isn't rotating, what is its angular speed? 0, right? There's no changes happening, right? Okay, so now I could spend the rest of the semester deriving the rotational version of the toolbox, or we can just sort of cheat. I'm going to cheat. Not cheat, but like skip over all of the mundane details. To get from the this linear toolbox over here, to the rotational toolbox, just swap all the symbols for their Greek versions. So instead of V, what are we going to write? Be careful. Omega. Okay? So we're going to write omega equals, and instead of V naught, it's going to be omega naught, which would mean what? Initial angular speed, right? Plus, and instead of A, we're going to write alpha, and instead of T, we're going to write T. The time is time. Okay? We're not going to put in tau or anything like that. Okay. Tau's different. Okay, so there's the first one. So on the second one, instead of delta x, what's position? It's theta, right? We're going to change the angle, right? And that's going to be equal to omega naught t plus 1/2 alpha t squared. And then for the third one, omega squared equals omega naught squared plus 2 alpha delta theta. Okay. What's happening here? What's happening? All that's happened is that the toolbox has gone to a toga party. Okay? Like, it's the first equation any different? No, it's the same equation we've always had, right? It's just the screwdriver has a different colored handle in this toolbox, right? Like, I can't stress this enough. I know it looks different because now it's all Greek. But the Greek symbols are just trying to clue your brain in to the fact that instead of the tire, like, translating, that's the word we use to say it moves in a straight line, right? Instead of going places, we're just going to be rotating it, right? It's going to be turning and rotating, and maybe it speeds up. It slows down, right? But it's a rotation as opposed to a translation. And do worry. We're going to put those two things together here in just a little bit. Okay, so let's, so what I'm going to do right now is I'm actually going to, I'm going to throw on some extra things just so that the entire toolbox is on one screen, okay? We're going to get to the rest of these things I'm about to show you in just a little bit. But for completeness sake, so we've got everything in red, right? So we've got the arc length definition. We've got everything under that in that red rotation box down here. Here's another one. The tangential speed that any object has as it moves in a circle is equal to r omega. What does that mean? Tangential speed. So where do people ride on the merry-go-round? So where do people like to be? Like when you go and you're racing for whatever horse you're going to sit on the merry-go-round, or the merry-go-round. They took all the merry-go-rounds out of the parks. Something about maiming children or something. So where's the fun place? On the outside or the inside? It's on the outside. Why is it the outside?
Greater radius.
They go faster. Okay? The tangential speed that something happens, right, has. Okay? So like if this object were rotating around that direction, okay, then I would draw the tangential speed, right, coming tangent to the circular path. At that instant, it has a linear v with units of, what are the units of v?
Meters per second.
Meters per second, okay, that are related to how far away it is from the center of the rotation times an angular velocity. What would the angular velocity be? What are the units of theta? Radians per second, right? So angular speed, we should probably write that one down, right? This is a radian per second. What would acceleration be? Radians per second squared. Just like meters per second squared, but instead of meters, it's a radian. Okay, so we have this relationship here between V tangential and the omega. There's a similar one. This is a new idea that you haven't run into yet, okay, called the tangential acceleration, which is r times alpha. Okay, so we talked about what alpha was, right? It was like the speeding up or slowing down of the wheel, okay? In order for alpha to happen, there needs to be a tangential acceleration that causes the change to happen. We studied before an acceleration that exists when anything moves in a circle. So if the speed is constant and it's just moving in a circle, what did we call that acceleration? Centripetal acceleration. Which way did that acceleration point? Inward. Centripetal is the word that just means towards the center, right? Okay. So all points on this wheel right now have a centripetal acceleration because it's going around in a circle. But if I speed up the wheel, if I slow down the wheel, in addition to the centripetal acceleration, there's a tangential acceleration now, something that causes the alpha to happen. Back in sort of the linear terms, right, our centripetal acceleration was v squared over r. There is a way you can put these two together. Okay, you can substitute in v tangential into the v squared over r equation, and you can actually get, a statement for centripetal acceleration in terms of omega. It's r omega squared. But just to point out here, okay, there's always been, because it's going around in a circle, a centripetal acceleration. But now, if alpha is also this way, right, then we will have a tangential acceleration, okay, that helps to speed up the wheel. So again, I just put that all, I'll show you some examples of all of this sort of thing. But I just wanted to make sure it was all on one page here for us, right? So we kind of had the complete toolbox, as it were, right? Arc length, basic definitions, our 3 equations, and then some added extras that I think of as the Google translation matrix, right? Like these 3 things here allow us to move back and forth, right? Velocity in meters per second, omega in radians, right? It's the linear version converted to the angular version, back and forth, right? So that's what those are hanging out. I'll demonstrate how to do that. Okay, what sort of hocus pocus is going on the screen? We do need to talk about another elephant in the room, okay? And it's the direction of rotation. I mean, X and Y was pretty straightforward. Just define a coordinate system, whatever's positive, you just go for it, okay? Which way is this wheel rotating? Counterclockwise, okay? From your point of view. But from my point of view, it's rotating clockwise. Do you see a problem?
Yeah.
Okay? Clockwise and counterclockwise depend on which side of the wheel or circle you are looking at. Okay? And that means that there's some like ambiguity there. We don't like ambiguity in science. We want precision in what we do. And so there is another way to talk about the direction of angular velocities and accelerations. And we define that direction by something called a right-hand rule. Okay? So I apologize to all the left-handers out there in the universe. There are no left-hand rules. Okay? It's just a right-hand rule. And so everybody raise your right hand. Repeat after. No, we're not going to do that. I'm just checking to make sure everybody knows which hand is their right hand. Okay, you can put your hands down. That's pretty good. You guys all pass. Right? Have I told you about the world's foremost philosophical expert on right and left hand? I haven't told you this? Oh my gosh. Okay, that must have been 2B. So one of the world's preeminent philosophers. Okay? This is a master of thought and idea and the implications of words and all that kind of stuff. His name is Winnie the Pooh. Winnie the Pooh said this, okay? Let's see if I can get the exact quote. I have no trouble telling my right paw from my left. It's knowing which one to start with that makes all the difference. Think about that for a little bit. You realize it's very deep, okay? And also strikes at the heart of every dyslexic person in the universe, right? So you need to know which one's your right hand to get this right. But what you do with your right hand is you take your right hand, everybody take your right hand, okay? Take your fingers, I call this the hitchhiker because you end up with your hand in a hitchhiker. You rotate your fingers around in the direction the wheel is spinning, and your thumb points in the direction of the angular velocity. So I wrap my fingers around. Okay. Really important. I forgot the safety tip. Okay? If you are causing yourself physical pain while doing the right-hand rule, you are doing it wrong. Mental and emotional trauma is okay. This is physics. But physical pain, if you're sitting there, you're doing it wrong. Okay? You wrap your fingers around in the direction naturally that they curve, and your thumb ends up telling you where the angular velocity vector is pointed. Okay, do this one. What do you have to do?
Turn my hand.
You got to turn your hand around, right, to be able to wrap your fingers going around, and now the thumb points towards me. Now notice, it doesn't matter which side of the wheel you are on. Your thumbs are pointing the same direction as my thumb, even though on my side it looks like it's going counterclockwise, right? Okay? So that's the power of this right-hand rule and defining an angular velocity's direction, not as clockwise or counterclockwise, but with this right hand. All that being said, we generally, if we're writing it down on a piece of paper, we just say clockwise or counterclockwise, right? Because it gets really hard to say in or out of the page or something like that, okay? But, not in this class, but in other classes in physics, we can now put this wheel in any orientation we want and have an entirely consistent angular velocity vector. So even if I held it like this, which way is the angular velocity pointed now? You wrap your fingers around, and which way is the thumb pointing? Up, right? Which way is it pointed now? Is that left for you guys? Okay, right? So that's the power of the right-hand rule. It is absolute. There's only one way to do the direction, right? And we don't. But that being said, we tend to just go clockwise or counterclockwise when we're drawing pictures. Okay. We just did rotational kinematics. So let's do an example, okay, of dealing with rotational kinematics. Okay, so hard drives still exist, still important. I mean, I know everything's like solid state nowadays, right? But in data centers and things like that, tapes are really still good, right? But hard drives for medium-term storage, SSDs, solid state for like need it right away kinds of storage, right? But maybe you still have a computer or something like that. It's got a hard drive in it. I got a little picture of a hard drive down there, right? Okay, and a hard drive has these plates in them. They're metallic glass plates that spin around, okay? When I was in college, I got a temp job, and the temp agency sent me to Seagate Technologies, maker of hard drives. And I was assigned, after they gave me an aptitude test or something, they put me in pre-sales technical support. So I was providing technical support to people that had not yet bought a hard drive. And I kind of looked at them and I said, how do I give technical support to something that doesn't exist? Right? They said, well, what you're doing is you're helping the customer figure out which drive they need for whatever their application is, right? Back in the day, it was a lot of server companies, right, calling us up. We need a drive to blah, 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 and it has this capacity, and we tell them which drive to get, and that was that. So I know what I'm talking about when it comes to the statistics of hard drives, okay? Very typical hard drive nowadays has a spindle speed of 7,200 RPM. And what does RPM stand for? Revolutions or rotations per minute. A revolution and a rotation is the same thing. One complete go around of the circle, right? But per minute, right? Okay. So what is that? What is a revolution per minute? Like what does that sound like? Is it an alpha? Is it a theta? It's an omega, isn't it? Omega is in units of radians per second. But instead of a radian, they're telling us a revolution, right? Okay, per minute. So we've got a funky unit here. But nonetheless, right? The omega final, right, in this problem is 7,200 revolutions per minute. I like to write it like that so I remember that it's an angular velocity of some kind, okay? Now, are revolutions per minute the standard unit for angular velocity? No, we need to get this into radians per second. So we've got to do conversion, which means we've got to go back to chapter 1, right? So we got to convert both revolutions into radians and minutes into seconds. What are we going to tackle first? Revolution? All right. So again, I'm going to do what I do in chapter 1. I'm just going to multiply by conversion factors, right? For every one revolution around a circle, how many radians is that? It's 2 pi radians. So there we go. We're not done. The revolutions are gone. But I need it in radians per second, not radians per minute, right? So for where do minutes go? Top or bottom? Good. And then 60 seconds on the bottom. So if I'm going to convert revolutions per minute into radians per second, I have to multiply by 2 pi and divide by 60. Or pi over 30. Okay? Whatever you want to do there. Where's my hard drive one? All right, so I converted that somewhere. 754 radians per second. And why did I convert to radians per second? Standard units, right? This is the standard unit for omega. Just like if we'd been given miles per hour or kilometers per hour, we are going to convert that into meters per second for our linear things. Well, when it comes to rotation, we're going to convert omegas into radians per second, alphas into radians per second squared. Now, did they give us, oh, darn it, they were mean again. I remember at Seagate, there was like these mixed units all over the place. It drove me insane. Alpha is 30 revolutions per second squared. So when you turn on a hard drive, turn on a computer, kind of older style computers, maybe you still have one that kind of does it. You turn on the computer, and it would do like some maybe flashy lights, maybe a beep. Okay, those are all ways for technicians to know whether or not like the memory was working or the CPU was working. Whatever. Okay, but then it would go like you turn it on, you'd hear the fans go on. And then you hear like a right? So what was going on is the hard drive was calibrating its head motor, and then it would start spinning up the platters. And it would take about 2 seconds, right, for the hard drive to go from inert to ready to send information in and out-ish. Okay? So at Seagate, we knew the spindle speeds and we knew what the motors were capable for accelerations, right? Okay. And then the engineers would calculate the startup time for the drive, which can be like pretty critical depending on what's going on. If you're hot swapping drives in and out, you want them to come up nice and fast so that they can start doing their jobs. So we are going to find the time. Okay. How are we going to find the time? Well, we've got a toolbox, right? Okay. And back when we did the linear version of this, do you remember like what our visualization step included? Like how did we organize our information? Anybody remember? We made a list, right? We made a list of all the things we could know and not know, right? And it came straight out of the toolbox, right? So there was omega, omega naught, alpha. So we'll put omega naught on the list. T, like again, I'm just kind of going through this box right here. And look, okay, I could know or not know omega. I could know or not know omega naught. Alpha, T. And then the next thing I'll get to is a delta theta, right? So I can put that in my list over here, delta theta. Okay. Do we know? Okay, so we know the final speed of the drive. Yeah.
Shouldn't we change alpha to radians?
Yeah, we need to convert. I didn't want to, so I just sort of was putting it off. We have a final omega. What's our initial omega? Yeah, it starts at rest, doesn't it? Okay, do we know how long it takes? Did they tell us a time? Yeah, we're looking for that, so I'm going to circle it to remind myself that's what I'm going for. And do we know, like, how far around, like how many radians the platters go while they're spinning up? Did it tell us a distance that the platters traveled? I don't see any radians anywhere. So, okay, so no, I don't know anything about that. We got to be careful about directions. So if we say omega is positive, goes from 0 to some number, what's the acceleration have to be, positive or negative? The drive's speeding up. It's got to be positive. So we'll make sure that we put a positive on there. We thought about it. Okay, I put it off long enough. I got to convert this. This isn't so bad. 1 revolution on the bottom, 2 pi radians on top. And I don't have to do anything with the seconds, right? Nice. Okay, this is 188.5 radians per second squared. Okay, check my units. Do I have standard unit? Yes, standard unit. Yes, standard unit. Yeah, okay, I'm good. Now I can do my strategize. We want to find time. We know omega, alpha, and omega naught. That's all we know. We want to find time. Which part of the toolbox are we going to use? First one? Yeah. We don't know delta theta, right? They didn't tell us anything about how many times it goes around, right? So I'm looking at this first one right here going, okay. I like it. So our plan is to use the first kinematic equation in its rotational form and solve it for what? Time. Okay, so let's move omega naught over. Let's divide by alpha. And so my time, I just went fast on the math because it's math. Okay, now I can chuck numbers in, right? My final omega, 754 radians per second squared, minus 0 all over 30 radians per second squared. 754 radians per second. There we go. It'll work out in time. And it's all standard units, so I'm pretty confident it's going to happen anyway. I got something I can't read because my handwriting is so bad. 4 seconds. I think that says 4.
I think the 30 should be the converted.
You were so right. And I'm so happy that there are electrons. Okay. So there we go. Thank you, Julia. All right. So there is my time. I don't know why my time got a little hot, but it did. Okay. So I found time, 4-second boot up time for this drive. Not so good. Want to boot up faster. Okay. What else are they asking me to do? Ooh. Okay, this is interesting. All right. So this seems like a little bit of a trick question, right? Like, how fast is a platter going when it's at full speed? Well, the answer is 7,200 RPM or 754 radians per second squared. Does it matter where we are? Like, does the angular speed change if we're like close to the center versus outside? As the wheel turns around, let's just look at this spoke right here, right? Does the amount of angle a point goes through down here, is that different than the amount of angle that a point up here goes through? Like if there was an ant here and an ant here, and we measured the amount of angle that changes in time, is that any different? No. Angular speed doesn't care about the radius, but tangential speed does. Which of these two ants, the one on the inner or outer, goes around faster? In terms of meters per second, the tangential v that the ant has, the further out you are, the faster you go tangentially. Again, the merry-go-round phenomenon, right? It's funner to be on the out. If you enjoy being whipped around and being thrown off your horse, right? Go on the outside. If you're going to throw up, don't go on the ride or go on the inside. So what this problem is asking, okay, how fast is the platter moving at these radii? Well, the uninteresting answer is they're both moving at 754 radians per second, right? Okay? But they want to actually, and they're not clear about it, they want to know speed, like in meters per second, right? That different portions of the platter are moving at. Why would we want to know this? Well, it turns out that hard drives, there's a difference in speed at which information can be read off of the platter. Where can information be read the fastest? The outside edge of the platter. because the outside edge is moving faster underneath the read-write head. There's more information going underneath it in the same amount of time than on the inner radius. So usually what happens is on a hard drive, there's like a limit, like there's an inner limit and then an outer limit where like data can be written. Okay? And so what we're going to do is we're going to calculate, right, the speed at 1.5 centimeters versus the speed at 4 centimeters, right? So how are we going to find, what's the Google Translate?
Radius times.
It's radius times whatever the other thing is, right? So it's going to be radius times omega. Well, the radius here is 1.5 centimeters, which we have to convert into meters. 0.015 meters times 754 radians per second, right? And this is a meter. So the units will turn out into meters per second. What happened to the radian? It doesn't have units, right? A radian is just a label. It's a tag. So when another unit shows up to take its place, it just takes its place, okay? All right, so 0.015 times 754 turned out to be 11.3 meters per second, which is approximately 25 miles per hour. So that's how fast data is moving on the inner part, the inner track of the drive. And then at the 4 centimeter or outer portion of the track, it's R times omega, but this time it's 0.04 times 754 radians per second, which turns out to be 30.2 meters per second, or approximately 68 miles per hour, right? So the outer portions of that drive platter are moving much faster tangentially than inner portions. And that's why data stored on the outer part of the drive can be accessed faster. Hard drives have logic in them that tries to put data that is accessed a lot of the time or is needed more frequently, it moves it more towards the outer edges of the platter. Whereas data that isn't accessed as often, a drive will try to get that data more towards the inside of the platter. There's a lot more to it than that, and I'm oversimplifying. But I wanted to just underscore this idea that where you are on a circle does change your speed in meters per second. Does it change your angular velocity? Is angular velocity different no matter where you are on the disk? No. But meters per second, the straight line velocity, the tangential velocity you have at that instant, that's very, very different. Seagate and other companies, when I was working back there, early 90s, were experimenting with faster and faster hard drives, and they were increasing spindle speeds. You can actually buy today 10,000 and 15,000 RPM drives. The problem with those hard drives, even though they are faster in terms of getting data in and out, they break sooner. We have this statistic called the mean time between failures. For a 7,200 RPM drive, the average time before the drive would fail would be 1 million operation hours. Okay? Like turn it on, leave it on for 1 million hours, you would get one failure. Okay? But as the spindle speeds go up, you start measuring mean time between failures in like thousands of hours. Like drives will fail much faster. And then they developed hard drives that they would spin the platters up so fast that the platters were exploding. And they were like, what the heck is going on here? It turned out that they had made spindles speed so fast that the outer edge of the platter was breaking the sound barrier, like going fast enough to break the speed of sound, while the inner parts of the platter had not yet gotten that fast. And so you're developing a sonic boom on the outer edge of the platter, while the inner platter still hasn't gotten to the Mach limit. And so it would set up this resonant, this wave, this wiggle in the surface of the platter, and the platter would literally shake itself apart. And so then they started playing around with, well, what happens if we put we pull a vacuum, right? We get rid of the air, and so there's no sound barrier. Okay, well, you can make a 40, 50, 60,000 RPM drive. And they're like, well, can we fill it with argon? And then it just turned out to be not feasible. right, to make them that fast. So nowadays, you want to go faster, get an SSD. You want to upgrade your computer and make it faster if it's got a hard drive in it, swap it out for an SSD. It's like free performance. It's really amazing. That's your Mr. Balogh tech tip for the day. All right, let's do a quiz. Gosh. 4-point quiz. Holy cow. I said it's been a while since we did a quiz. Trying to make up for lost time. All right. 8.1, 8.2, 4-point quiz. And it's 4 points because it has 4 questions. Two points on this disc, right? P and Q. P's on the inner, Q's on the outer. So you're answering 4 questions. Which point, P or Q, has the bigger tangential speed, meters per second, or angular speed, radians per second? And then 2 more questions. Which of these undergoes the greatest change in arc length and change in angle? You're telling me the greater of the 2 in each of those questions. So 4 questions, 4 answers, 4 points. Give you 30 more seconds. All right. Turn to your neighbors and tell them your 4 answers and why you chose what you chose. Go.
Okay, so for the change in angle, I think the same.
You're starting from the bottom?
Yeah.
Okay, change in angle. Yeah. The
Yeah. How would you say for arc length?
arc length. I think you would have to think so you're looking at so like the size of the circle. P has a small, like if you're following that line, that's small. Tangential speed.
Oh wait, no, no.
So Q. Angular speed, I'm not sure actually about that. Change in angle, so it's like, oh, they're the same. Like, wait a second. I can't remember the
Just say Q is just bigger. I'm just gonna like Q is bigger for all of them. You know, Q is bigger for all of them. Okay. Except obviously the arc length, and then we said that they were equal and the change of angle. So.
Can you remember how the equations?
All right, I think you got it. Two of these answers, P and Q are the same. Only two. Which two of these are P and Q identical? Angular speed, right? Doesn't matter where you are on the merry-go-round, your angular speed's the same, right? What's the other thing that's the same? Change in angle. If the angular speed's the same everywhere, then the change in angle has to be the same everywhere, right? So for those two answers, P equals Q or none, or like, it's not one or the other. Okay, so which one has the greater or largest tangential speed? Q, excellent. And which one has the bigger arc length? Also Q, right? Because arc length, S equals R theta, right? The arc length depends on where you are, how far away from the center you are. And as far as angular or tangential speed goes, tangential speed is R times omega, right? Again, that radius, where you are on the circle, determines what the velocity is going to be. All right. This part is going to feel like a little bit of hocus pocus, I'm not going to lie, because I just need you to believe something, okay, and take my word for it. So what we want to do is we want to study, so up to this point, we've just basically been spinning a circle, a wheel in one spot, right? But now what we have to do is we have to do rolling motion. So a tire, right? Rolling along the ground. This rolling motion, first of all, requires friction to exist. If friction didn't exist, what would the tire do? It would just do this, right? Okay? It wouldn't need to turn at all. There's no reason for it to turn without friction. And what kind of friction do we want to have between the road and the tire? Static. So in this case, static friction is helping us with the rolling motion. And when we get to it next chapter, we're going to come up with a new kind of energy that this is going to have called angular or rotational energy. Okay? So we are going to do the case in Physics 2A, a tire or a wheel or any object that's rolling, like a bowling ball, anything, it will roll without slipping. Okay? That means, that the tire will always have static friction between the road and the rolling object always has static friction, okay? And that static friction is helping it to turn. It's not taking energy away or doing any of that kind of stuff, okay? So just real important to understand that we need to have friction here in order to have rolling motion. Okay. For something that is rolling, and let me draw another circle here. Please make a good circle. There, good circle. Okay, right? And it's like rolling along the ground, okay? And let's say it's like rolling that way, okay? So turning. Which way is this object going? If it's rotating what looks like clockwise there, which way would this thing be moving? To the right. Now, it gets really awkward when we start talking about, right, this thing rolling to the right. Like, what part are we talking about rolling to the right? Because, the top part of the wheel is moving to the right, isn't it? But what's the bottom part of the wheel doing? The tangential velocity is to the left, isn't it? Right? So what I'm trying to say here, right, is that if we look at... No, come back. If we look at, like, the top, the top's going that way, but the bottom is going... And what's this side doing? Right? And this side? Right? Tangential everywhere, right? So how do we talk about the translation or linear motion of this wheel? We talk about the center of mass motion. okay? And so we have not talked about center of mass. It was in chapter 7. We're going to do a whole lab on it next week. But you guys already know what center of mass is, right? Okay? It's the place on an object where gravity seems to be acting on it, right? It's the place where if you added all the mass together, if the object is uniform in shape, it would be in the middle, right? So unless you're told otherwise, center of mass is going to be in the middle of things, okay? So this wheel has a center of mass. And that center of mass has a velocity. And what I wrote there was V sub COM, center of mass, right? And that center of mass, right, will be moving to the right. Even though all other parts of this wheel could be going in whatever direction tangentially they're going, the center of the wheel as it rolls, right, the center part right here, if you look at this axle, okay, is going to the right, isn't it? Okay. We look at that center of mass motion. It turns out that the velocity of the center of mass, if the wheel is rolling without slipping, is equal to the radius of the wheel times the angular speed of the wheel. So this looks exactly like our tangential, like our Google Translate, between tangential velocities and angular speeds. It just so happens, we do all the work and derivations and stuff, that the center of mass speed of the wheel is also equal to r omega. It's just a kind of a happenstance. It's like an average velocity for all the parts going around. All right, but if this, let's just do some what ifs, okay? The center of mass, let's say the center of mass is going, 10 meters per second to the right, okay? What's the speed of the wheel at the bottom? The whole wheel is moving to the right, isn't it? But it's also rotating, right? So the bottom part can be thought of as moving to the right at 10, but it's also rotating around. And what must the speed of the point of contact between the ground and the wheel be in order for there to be static friction there? It has to be 0. So if you are driving your car at 60 miles an hour on the freeway, how fast is the bottom of your tire going where it meets the road? 0. And how do you know that? How fast is the ground going? 0. And in order for there to be static friction, what must the two surfaces be? Not moving relative to each other, right? So what does that mean the speed of the top of the tire is? Double. This is 0, and this would be 20, right? So different parts of your tire are actually moving at different speeds. And it gets even weirder on the edges. Don't draw this, okay, because it doesn't matter. But this one has got a downwards, whatever V tangential it would have, and a sideways one. So it's actually moving that way when we put those components together. And over here, it's moving up and this way, so it's like going there. So like the tires in your car have to be engineered to be able to withstand this constant change in tangential velocity, right? Even though the angular velocities are all the same. But when it comes to things that are rolling, we can relate the center of mass, speed, which is measured in meters per second, to the angular speed that rolling object has to have in order for it to stay rolling. So let's do an example here, right, where we've got objects that are both rotating and translating, like the tires of your car. Like if your car is going 65 miles an hour, what must the center of mass speed of your car be? Of the wheels on your car? It has to be 65, right? Because if your car is going 65 and your wheel's center of mass is not 65, what's happening?
Terrible.
The wheels of your car are coming off, right? Like you want all of the parts of the car to be moving, their center of mass speeds to be moving at the same speed, okay? So these are boundary conditions that we put on problems that say, look, we can't have wheels moving faster than cars and all that kind of stuff, right? Now, this problem, like at face value, kind of sounds like a chapter 2. I mean, look at it. They're giving us meters per second, right? It's acceleration. I mean, this car is going in a straight line, isn't it? So we can solve this problem by doing an old chapter 2 problem and then converting our answers at the end. Or we can convert at the beginning, get everything into angular terms, because they do want us to find revolutions, right? Okay? And they want us to find final angular speed. So you can actually do this either way. It doesn't matter. So I leave it up to you. Maintain the illusion of democracy and free will and choice. What do you want to do? Do you want to do this problem linear first and then convert to angular, or just convert to angular and keep it in angular? Convert first?
Yeah.
Let's get some practice in just doing the angular stuff.
Yeah.
I like it. Okay. So if the wheel, and sometimes I just visualize this by drawing a circle and then saying, okay, the center, right? I could give it a vector. This is 22 meters per second, right? That's my velocity of my center of mass, right? Knowing that that's my velocity of center of mass, I can find out what the omega is, right? Because like I just taught you, the center of mass velocity is related to the angular speed of the tire through this thing that looks an awful lot like the tangential version, right? It is the tangential. It just happens to be the same thing. Okay, so let's see here. I'm solving I'm converting, right? So I'm trying to find the things that I could know or not know, right? In my list of things that I could know or not know from rotational motion, right? And do we know what the omega naught would be if it starts at rest?
0.
Yeah, it's 0, right? Okay. And then we're going to go find omega final by taking the V center of mass and dividing by the radius. And this is where I'm going to screw up, because what did the problem give me? It gave me the diameter. I hate this. How many times have I put 58 centimeters in thinking it was the radius, right? What do I have to do with that? Divide by 2. Well, 0.58 meters divided by 2 to get the radius, right? I don't know what that number is. Apparently, I didn't do it this way in my notes. What is it? 0.29 meters. Okay, so there's the radius. So V center of mass, 22 over 0.29. I did do that somewhere. 75.9. Radians per second. And unwittingly, I mean, knowing that this is 770, what did I say? 75.9? Did I write that down? Yes, 75.9 radians per second. Unwittingly, I just did part B, didn't I? What's the final angular speed of the Oh, they want revolutions per second because they're being idiots and rude and all that kind of stuff. So how do I get my 75.9 radians per second into revolutions per second?
1 revolution over 2.
Okay, yeah, what goes on the bottom? Why does radians go on the bottom? Trying to cancel out the radians, right? So, and then on top I want revolutions. So for every 1 revolution, how many radians are there? 2 pi. I did that, I got 12.1. revolutions per second. So there's the answer to B. Part B. Okay, back to part A. Okay, let's see. Do we know anything about the acceleration? I mean, we know it's uniform, meaning it's nice and even and smooth and constant. But they didn't tell me a number, did they? I'm not seeing one. Do we know how much time?
Yeah, like 9 seconds.
It says 9 seconds, right? And they want it, the number of revolutions. That would be the angle. We'll solve for it in radians, then we'll have to convert. Okay, so what can I do? Which of my toolbox equations so what do I have? I have omega and omega naught and time. Every equation that's got delta theta in it also has alpha in it. So what am I going to have to find first? I got to find alpha. Like, I can't help it, right? The second equation's got alpha in it. Third equation's got alpha. The first one's got alpha in it. So I got to find alpha. I can't just ignore alpha, right? So is there a way to find alpha if I just know these four things? Which equation is that? It's the first one. So use the first one, solve it for alpha. Let's do that right now. Omega minus omega naught over t is going to be my alpha, which is 75.9 minus 0 all over 9 seconds. I got something that I don't know because I didn't calculate it. 5.9 divided by 9. 8.4? Oh, it detected it. It detected it as 75 times 9.
Divided by 9.
What was it, Brandon?
8.4.
Thank you. Radians per second squared. Okay, now that I've got that, which equation can we use now? Now that I know that this is 8.4 radians per second squared. Second one? Why not? That means I don't have to do any algebra, right? So use the second one, which is, I never remember these in their Greek form. I'm literally thinking delta x equals v naught t plus 1/2 at squared, and I'm just writing the Greek letters down. So sometimes you'll hear me say delta x equals v times t plus 1/2 at squared, even though I'm just writing the Greek versions, right? Okay. Looks like I know everything, right? Omega naught is 0. Oh, that's nice. Plus 1/2 times 8.4 times 9 squared. I got this as 340.7.
341.4.
Okay, 341?
Yeah.
We'll meet in the middle. 341. What units would this be in? If standard units went in, what are the standard units coming out? Radians. Now, did they ask me for radians? They asked me for revolutions, didn't they? So how to convert from radians to revolutions? 2 pi radians in 1 revolution, right? So we divide that by 2 pi, and I got 54.2. So this car, in going from 0 to 50 miles an hour-ish, 22 meters per second is about 50 miles an hour, the wheels on the bus go round. The wheels went around 54 times, right? To enable that to happen. Okay? So again, if something is rolling, just you've got the new center of mass relationship to deal with. but it turns out to be the same mathematical thing as a tangential speed. I did it, 10:45, right? Chapter 8, all done. Okay, so what's going to happen for chapter 9? 2 days next week, Tuesday and Thursday, we're doing chapter 9. We've got to do energy, we got to do Newton's laws, and we got to do momentum. And then we will take a test the week after that. Like really fast, isn't it? We just did chapter 7 and 8. Chapter 7 homework is due Saturday, right? Chapter 8 is due the Saturday after, and then chapter 9 is that Wednesday. So get 8 done as fast as you can, right? If I don't see you tomorrow in Grasp, have a great weekend.
After correcting all the answers. 16 times.
Good job. Good job. How did it feel? Good.
I have a high school.
No, like missing out on.
He lets you do it during
That does help.
I didn't join yet, but I do have. I tried starting as much, but only still with 8 courses.
Yeah.
It could very well be just the name.
Yeah, hey man, thank you, I appreciate
It
it.
is. Okay. 2 sections. 2 sections. Just me, my name on it.
See you later. See you, bro.
No, there was only 2 this summer. Yeah, we get a lot of like students that don't have to take
Last time, yeah, I don't, yeah, I don't really have to.
I wanted to take this with you, but it took it. Class for the semester. So now I'm taking a little bit. Actually, I was wondering about that. So
Yeah, no, I'm probably the only one.
Yes.
thank you.
Have a good weekend. What time do you like? I'm your best
I get there at 7 in the morning. You don't have to be there either way. I'm there from 7 to 11. Yeah. How'd it go yesterday? Yeah? Good interview? Oh, great. Right, yeah, no, absolutely, very important.
About like.
Yeah.
Yeah.
I'll probably get there later on.
Sounds good?
Yeah.
Yeah. It's our, it's NS1. It's right next door to our lab room.
Okay.
Yeah. If you walk into our lab room, all the chemists will be in there, you'll know you're wrong. Did you find anything out?
Yeah.
What they say? Give me 1 second.
Water, right?